Look at this split screen. On the left, a premium x86 Field laptop. On the right, a flagship smartphone wired to a USB-C hub. We are launching identical, heavy network exploitation scripts on both machines at the exact same moment. If your hardware drops offline or loses power halfway through a site engagement, you have completely blown the audit. If you are an enthusiast, the stakes are measured in your time. You have to decide whether to sink weeks into custom compiling mobile kernels or just boot up field-tested laptop infrastructure that works out of the box. To separate the educational novelty from professional utility, we have to bypass the software aesthetics. We need to stress test the raw, low-level engineering boundaries of both systems. This matrix will track our results. We are starting with the first pillar, evaluating software parity. When you use an advanced Droid virtualization environment like Termux, your Android device can achieve near-identical software execution to a full desktop Linux build. But this exact software match creates a false sense of security. The terminal looks right, which masks the fact that the mobile environment lacks physical access to the device's internal networking chips. This diagram illustrates the physical divide between Arch64 mobile architecture and x86-64 desktop architecture. Think of the ARM architecture as a high-speed conveyor belt, optimized to continuously move thousands of identical calculations using extremely low amounts of electricity. The x86 desktop processor is an industrial forklift built to consume massive power to brute force heavy hardware instruction sets. When you drop a complex x86 workload onto that mobile conveyor belt, the entire mechanism seizes and halts. While your software interfaces might look identical, forcing a mobile processor to handle erratic desktop-level workloads will inherently crash the system. Software parity passes, bringing us to our second testing pillar, hardware driver access. There is a common misconception that installing Kali grants instant, plug-and-play access to wireless auditing and monitor mode. A desktop Kali installation loads all known wireless firmware blobs by default. Mobile Linux builds have to aggressively purge those networking packages to prevent memory bloat on restricted mobile storage blocks. If you actually want to enable physical wireless packet injection on Android, you have to aggressively rewrite the standard Wi-Fi drivers with custom-compiled binary files, like the QCA-CLD3 module. This creates a constant tug-of-war. Operating system engineers push updates to isolate system processes, while open-source developers continuously hunt for kernel hooking side doors. To install these custom drivers, you have to permanently break your phone's factory security chains by unlocking the bootloader. To transform a smartphone into an offensive auditing tool, you have to paradoxically render your own physical hardware highly vulnerable to local compromise. Driver access earns a conditional pass, leading to our final test, peripheral interaction and the hardware bus. This cross-section shows exactly where the mobile setup breaks down. The true hardware bottleneck isn't the processing chip, it's the motherboard's communication pathways. A laptop effortlessly distributes network traffic, keyboard inputs, and power across completely separate internal hardware buses. A smartphone has to aggressively funnel raw power input, multi-device data traffic, and external networking signals through a single glowing red USB-C choke point. This triggers the failure in our real-world stress test. We initiate a heavy, automated wireless attack suite through a USB-C link connected directly to the phone. The mechanical failure happens fast. The rapid, erratic spike in data and power draw triggers the phone's internal battery management system to panic. To protect itself, the smartphone instantly severs power to the external network card, dropping the device entirely offline. Until mobile motherboards are designed to independently juggle massive external power loads and multi-device data traffic, an Android phone can never guarantee the continuous physical reliability of a desktop workstation. Which brings us to the final engineering verdict. Look at this chart. An Android phone cannot natively replace a desktop setup, but it functions perfectly as a highly specialized auxiliary edge instrument. The fully customized Android device drops directly into the physical stealth quadrant. For a professional running a close-quarters physical site assessment, A modified phone offers unparalleled visual deniability in spaces where a laptop would instantly raise suspicion. The x86 laptop maps directly to the opposite corner as your primary workstation. If you're an enthusiast or student, rely on standard x86 laptop infrastructure for your primary lab. You will save yourself weeks of troubleshooting low-level kernel bugs. Desktop architecture also maintains the permanent advantage of instant hardware swaps. You can upgrade RAM or change an internal Wi-Fi card in minutes, compared to mobile's rigidly soldered system-on-a-chip layouts. But the rapid consolidation of ARM-based desktop processing, chips like Apple Silicon and the Snapdragon X Elite, signals that this architectural divide is actively dissolving. True professionals do not base their toolkits on romanticized hacking illusions. They map the hard physical limits of their hardware directly to the specific tactical realities of their environment.